So this brings us to the next topic, which is recursion. Let me just there we go. So yes?
I have a quick question about that, because you have a number that you pass in when you have a string formatter. Is it possible to pass in a string?
No, it's not that good. Yeah, once again, Faust provides you with the basic element to make user interfaces. So you can create basic user interfaces, like with basic names and basic things. If you want to make something more complex than that, you should just write your own user interface at the top of the Faust code. Yeah. So no, just just numbers. Okay. So now you're gonna have to be fully operational, because that's the hardest thing we're gonna do during the entire workshop. So you guys, there is something that you don't understand, you have to stop me and ask me to repeat it again, because what we're gonna do now is the hardest thing to understand in Faust. Okay. So we know a lot of things now, and we can actually create a lot of audio effects with what we have. One thing that we don't know yet is recursion. Why would we need recursion? Okay, so yesterday we saw how to make delay. Okay, I'm standing in this room and talking to you. The sound coming out of my mouth gets to you with some kind of delay, so the guys who are in the front probably hear me a little bit before the guys who are in the back, and that's how it works, right? The thing is, in the real world, most of the things that happen at this level happens with reflections, right? So if I talk now, the sound of my voice travels at the back of the room, it is reflected, and then it comes back, right? If I do that, then I create an impulse. The impulse gets on the walls and is reflected. Okay. So far, with what we know in Faust, we don't know how to do things like that. We know how to add the delay to a sound, so that if I go outside in a place where there are no walls, no trees, nothing, if I just clap my hand, then the sound travels, but it never comes back to me, right? So now we're going to learn how to make the sound come back to you in Faust. So we're going to learn how to make feedback, which is basically create recursion, so that things are reflected, and so that you can send elements of your algorithm, so signals in your algorithm, back to one place in the algorithm. Okay. So in other words, if I have a function, the input signal is x of n. Okay. This signal is outputted somewhere. What I want to do here is I want to take the signal here and then send it back here and add it to the current signal. Okay? So recursion. Want to send things back in time. How do I do that? Okay. So in Faust, there is a specific signal operator for that, which is the tilde operator. So I'm going to create a new process. And my new process for now is just going to take an input and copy it to the output. So what I want to do for now is just that, okay? So take x of n, my signal here, send it back. To do that, I'm going to use the tilde operator, okay? So the tilde operator implies a split, okay? So the tilde operator is going to say, send this guy back somewhere, okay? But it's also going to create an automatic split so that the signal of tilde that I have here continues to go forward, okay? So my tilde operator is going to split my signal so that part of it goes on that side, part of it goes on that side, okay?
Does the energy stay the same with each one or divided by 2?
No, it's the same. It's a copy. Then I'm going to have to put another tilde in here, okay? So this signal that I'm declaring here is the feedback. So it's basically the signal that I have in here. So that signal here doesn't contain that anymore, okay? So that part is done. We're done with it. And it's going to the next step, okay? And that guy here is the feedback. So it's, yeah, this signal here, the signal that starts here, you know, and that gets returned on the other side of the algorithm. Okay? So far, so good. We're very close. If I try to compile that, it's not going to work. And the reason why it's not going to work is because now I'm returning a signal back in time. Or not in time, but back in the algorithm. And this signal has to connect to something. The problem is that it doesn't really have anything to connect to for now. So what I have to do is I need to add a plus here. Okay? So in other words, okay, I'm gonna save that and display the block diagram, and we're gonna go over that once again. There we go.
So it's real time. I mean, it's a real plus.
Yes, absolutely. So, so plus has two arguments, right? Plus expects two arguments. So plus has two inputs, okay? 1, 2. 1 is basically filled by the signal that we're sending back in time, okay? So what the tilde operator does is that it's going to send the signal back on the other side of the algorithm, and then it will connect to the first thing it finds, okay? And for instance, the first thing it finds here is one of the inputs of my plus function, of my add function, okay? But then I only filled one of them. Like my add function has two arguments. One is filled with the feedback. The other one is free. Because I'm in process, automatically the other one is turned into an input.
Is that an implied delay, or is it literally becoming?
Yes, yes, absolutely. So that's what I'm going to say after that. And as I said, the split, the tilde here, so my feedback operator implies that my signal is split into two different signals. So one is going, and it's going to the next step. There is no next step, so it becomes an output. And the other one is actually my feedback. And as Richard mentioned, in here, there is an implied one sample delay. Yeah.
Will it always hook to the first input of the thing which is before?
Yeah.
So it's not, if you had put 1 plus, then the compiler will complain. But if you put +1, it will accept it.
Yes. Look.
Can you describe again the underscore after the tilde?
So the underscore after the tilde is just an abstraction in that case of this signal in here. So if I want to put operations here, I will replace the underscore by those operations. So let's say that, for example, I want to multiply this signal here by 0.9, for example. I will replace the underscore by multiply by 0.9 operation. Now if I save that, it still works.
So you first multiply, then you choose tilde to get it back, and then you add, right? So the order of the operators is...
Yes, so everything that happens on that side of the tilde is what is happening at the bottom of the block diagram. Everything that happens on that side of the tilde is what happens in the feedback.
It's like a prefix order.
Yes. Yeah. And I'm actually going to have, I'm going to have to put parentheses here at some point, because if I want to make more than one operation, I'm going to have to put parentheses in here so that all the operations that I do here are the operations that are happening in the tilde. So for example, if after my multiply by 0.9, I wanted to add 0.3, I really need the parenthesis in that case. Otherwise, it's going to break. And there we go. Yes?
So, sorry. So, the tilde send the signal back to the plus.
Yeah.
For the first argument or the second one?
The first.
The first.
Yeah. What happens is that tilde send the signal back. Okay. Then the signal is looking for somewhere to plug into, right? And it will plug into the first thing that it finds, like the first available input. For instance, the first available input that it finds is the first input of the plus operator. Okay, so it plugs to it. But then, because there is one left, and that is free, this one automatically becomes an input signal. Because we're in process. Okay? So that is the hardest thing to understand in Faust. And especially when you come from imperative programming languages, and especially if you, it takes some practice before you really get used to that kind of syntax. Once you have it, and once you really understood it, it's very powerful because it's actually very convenient. And, but yeah, Nando?
Why is there one sample delay? That messes up anything that you try to do in terms of filtering or anything, right?
That's...
because it could very well just take it back in the same processing cycle.
That's...
So there is actually a one sample delay, or?
It would be an infinite or something. It would become an infinite loop if you had zero delay.
Well, the thing is, I mean, it's not... What happens is that the output of... on the C++ side, the output of, well, that gets copied into a buffer, okay? And this buffer is only read the next time, right? You know what I mean? Because there is absolutely no way, because it's too late, basically. This operation was already.
You have to have a buffer.
Yeah, that's the.
Yeah, it would be pointless otherwise, right? Because I mean, you might as well just have that function on the inside or the head of the adder.
Sure.
Represent the signal, modified and not modified in the same manner.
Yes, because the thing is, I mean, it's if you look at this algorithm here.
So Faust is not really completely magic.
Yes. No, but that's actually very no, but I mean it's a very good comment because it's just that once this operation, once the plus has been done here, well, I mean you can't really go back in time and do it again with what you have to wait for the callback function to go to the next cycle basically.
If you're making reverb and stuff like that, when you want that.
Yeah, I mean. You always want that. That's it's just that I mean once because at the end everything gets computed linearly because it's in C++. So and then it goes back at the beginning and do it again and again and again. Yeah.
So the tilde creates one sample delay for the plus.
It creates an implicit one sample delay because I mean it's a very weird one sample delay if you think about it though, because it's a one sample delay, but there is no other way basically, right? Because once you did, okay, let me remove that and draw the block diagram again. Okay, so. If there was not a one sample delay implied by the feedback, it would mean that once you computed the plus, like operation here, okay, and then send that back in time, you would have to recompute the plus again, and then wait and then redo it basically, which is not how things work in the real world, right? So it's an implicit one sample delay, because you basically have samples coming that way, right? So like first sample, second sample, etc., etc., etc. So when the first sample arrives here, it is added with the feedback. By default, the feedback is going to be 0 for the first sample, right? Then it's going to do, so the first sample is 1. The result of this operation is going to be 1 plus 0, so it's going to output 1, right? And then 1 is going to be returned. And then once the second sample is going to arrive, then the second sample will be added with the previous sample, so there is a one sample delay here, right?
You didn't like the number of samples like you did with the single quote?
What?
Can you have the delay be more than one sample?
Oh yeah, of course, yeah, no, absolutely. And that's what we're going to do later. It's just that let me.
This recursion really is not in the sense of algorithmic recursion in a traditional language.
No, well, no.
To model real hardware where you in a loop, it cannot be 0 time. Otherwise,
Yeah, absolutely.
it's break.
Yeah. If there was not a one sample delay in here, if we had to write like the differential equation of what we're doing here, it would be y of n, okay? And y of n is basically equals to y of n plus y Sorry, yeah, sorry. So it would be x. It would be x of n plus y of n. So y of n is the feedback, right? Y of n.
So it has to be minus 1, otherwise you will not be able to compute it.
Exactly. That's the thing. Otherwise, it's not possible basically, because it's not possible in real time. That's the thing. If you can afford to not have a one sample delay in here if you're not computing things in real time, because then what you can do is that you can have a delay in here that is going to match the two things together, you know, and you're going to have to add a one sample delay in here to make sure that things are, so that you can do. I mean, what you can, yeah. What you can do is that if you really want to get rid of the one sample delay, you can add delay in here so that the two guys are in phase basically, you know, and arrive at the same time. But the problem is that if you don't do that, then you're okay. The thing is, so those are pretty technical questions. For now, you just have to assume that there is a one sample delay in here, and
Actually, you can't get rid of them, right?
No, that just pushes backwards in time.
If you put one sample delay for the input message,
yeah.
it will be the whole thing one sample delay.
Yeah, that's it. Yeah.
But you can't really
Yeah.
avoid.
No, you can't. Yeah, there is no way. Yeah.
No, and I mean, if you really thought you had to do that, you would just basically split the signal, run the algorithm on one of the signals and merge them.
Absolutely. Yeah.
It's the same thing.
Yeah. Okay, good. Well, I mean, you could get rid of it, not in Faust, in the case where your algorithm would not run in real time and where you would know one sample in advance what your signal is going to be, basically. And in that case, you could do that. So you'd have to know one sample in advance what the future will be, basically, which in real time is not possible to do. Although there are tricks, because there are cases where you actually need to know in some ways what the future is going to be for your algorithm. And do you have actually, can someone think about a plugin or an audio effect where you need that? Because there is actually one where you need.
Yeah, I think there's a reverse something I remember.
Something that is used a lot by sound engineers.
Look ahead.
Absolutely. If you have a compressor with a look ahead, you need that because we're not going to do that because that's like Faust plus. But if you build a compressor that has a look ahead, you actually need to know a little bit in advance what the signal is going to be, right? And so that's a typical case where you need to know in advance what. And the reason why you need a look ahead on some compressors is to make them even more effective. Because if you know what the signal is going to be a little bit in advance, then you can optimize the compression algorithm so that it's gonna be as efficient as possible in terms of just increasing the signal when it has to be increased and reducing it when it has to be reduced. So, yeah.
How much time ahead do these compressors look?
Not a lot. And it's like, it depends on how your algorithm is implemented, but ideally as less as possible because otherwise you add a little bit of latency, right? But then you can use like some prediction algorithm to kind of know what it's going to look like, you know. But in general, it's not. It's like a couple of samples, basically. So, yeah. Okay. So, back to. Do you have more questions about that, or actually at least about the notation, because that's very important. So this thing is totally self-contained. Once I've done that, I can carry out any operations that I want after it. So I can put like colon, and I can put multiply by 0.5, for example. Okay, save it. And then if I look at the block diagram, it's kind of what I expected, right? So this is done here. And then because we said that the tilde splits the signal into two signals, one of the signal is moving forward and gets connected to the next operation, okay? So just to summarize everything, everything that is happening in here, so between this point and this point, has to be on that side of the tilde between parentheses. Here there are no parentheses because we're doing only one operation. If I wanted to do more than one operation, I would put parentheses, okay? So if I put parentheses in here, I can do a plus, then I can connect my plus to I don't know, I can multiply by 0.1, you know, any kind of operation that I want. Now I can save. I can look at the block diagram. There we go. Okay, so everything that I put on that side of the tilde between parentheses, any operation can be a function too. It can be just so if I don't want to write everything directly in there, I could create a function before it that does it for me. I can put everything I want on that side of the tilde, and what is on that side of the tilde is what's going to happen between here and here.
And if on the right of the tilde I have, for example, something that generates two signals, what will happen with the two signals?
So if you do that, then it's fine. You just have to make sure that on that side of your algorithm you have 3 inputs, right? Okay. Because the signals are, you know, they are sent back, and what they do is that they connect to the first thing that they find. Okay, and so one of them is going to connect to the first thing I find, and the next one is going to connect to the next thing, you know. And if it has nothing to connect to, it will break because then Faust doesn't know what to do with the signals. And then everything on that side of the tilde is everything that will happen at this level here. You know what, Nando? There is, so I got a counter example of that, and it's actually a totally insane example. So I think you know him actually, but there was this undergrad, Matthew something. He's blind. Yeah. You know, and so he can't see block diagrams, and he really got into Faust this year. And he managed to rewrite some of what Aaron Heller for the ambisonic decoder. Yeah. And that's what I'm going to start looking at now. Yeah. And this guy couldn't see block diagrams. And he was actually totally fine with that. And I don't know how he did it. I don't know how he did it because he couldn't see block diagrams. So the only thing he could see was that, or actually he couldn't really see it. He could feel it basically. So it's crazy because this guy had basically had to buffer that into his brain, you know. And once he buffered that into his brain, he had to find a way to connect things together virtually in his brain, which is like really, really, really impressive to me. And it was crazy because I worked with him like for a couple of days, and he could read the Faust code faster than I did. Like when I was reading the beginning of the function, he was already at the end basically, and he already had it, you know, so no, it is possible.
His brain was oriented to processing sequential things like language.
Yeah, exactly. Yeah, it was. It's crazy. Well, you know, I'm working on this project with Sheila over the summer, and she's gonna have to use Faust a lot. So I hope she won't get that, because that's and Sheila is blind too. So.
You can write for a component that creates a 3D diagram. It would be like Braille.
Yeah, well, so we had this idea for a while. I mean, someone should do it because it's kind of a beautiful idea, you know, but you can represent lambda calculus with shapes where you have like cubes, pyramids, you know, and things like that, you know, and by putting a cube in a pyramid, you're going to create a new shape, you know, which is so it's like a crazy approach to functional programming language through 3D shapes, basically, you know, and so we had the idea of maybe one day creating a user interface for Faust that would be just based on that. So instead of building your algorithm with code and with things like that, you build your algorithm with 3D shapes. So I don't know how useful it would be because it would be probably very impractical, but it would probably be very beautiful though, you know, like because you're basically coding with 3D shapes, and that's something that you can do because lambda calculus, the paradigm of lambda calculus allows you to do things like that. So, yeah. Good. Okay. So we're good with that, right? So we're gonna see a couple of more practical examples of that. So the most practical example that we can see for now is the case of an echo, right? So when you're standing at the top of the mountain, it's you. Okay? And there is a bigger mountain in front of you, or even if it's smaller, it's fine. It should still work. But maybe there is another mountain behind you, okay? What happens is that, you know, you scream, and then it takes some time for the sound of your voice to go on one side. And once it gets there, what happens? It is reflected back. And it goes back that way, and then you hear it, and then, well, it is reflected in the back, you know, and then things get messy. So that's something that we experience all the time, everywhere in the real world. We're experiencing it in this very room, especially in this room that has very parallel walls. So depending on where clap my hands, I might hear actually the reflection of my clap bouncing back and forth between the two sides of the room, right? So now that we know how to do that in Faust, we can actually create things like that. Yep. So just one little detail before we go into actually making things out. So when the wave that I created with my voice travels and hits the mountain and is reflected, something happens to my wave. What is it?
It loses energy.
Well, there is that. So we're going to have to take that into account because the mountain is going to absorb some of the energy created by my voice. So the wave that will be reflected will be less powerful than the wave that I sent, right? And it's also losing energy in the air too, right? But there is also another thing that happens.
Well, of course, it's time factor.
What?
There's time factor too, there's a delay because
Yeah,
it's
sure.
to travel there and travel back.
So there is the time, but when the wave hits the mountain and is reflected, not only the wave lost energy, something happened to the wave.
It lost frequency.
There is that too, but that's like the next level. There is something more fundamental that happens to the wave when it hits the mountain.
Phase reflection?
What?
A phase reflection?
There is a phase thing that happens. The phase of my wave is inverted. And phase inversion in signal processing is done by inversing the sign of the wave. So it's actually the same thing that on a guitar string, basically. If you think about a guitar string, okay, the guitar string has two rigid terminations. Okay. If you take the string, you bend it, okay, and then you just release it, then it's going to start vibrating, and etc. And then the waves are going to travel across the string and being reflected on the terminations, right? And so if I have a wave that arrives here, you know, and the wave has this shape, so that's the rigid termination, okay? So when the wave is going to be reflected at this point, what is going to happen to the string? The string is going to do something like that, right? And so when the wave is going to be reflected, the string, instead of being here, is going to be here, right? So if this was a sine wave with gain 1 minus 1 here, okay, when it is reflected, I change the sign of it, right? So the same thing happens with the mountain, and the same thing happens with the wall of this room. The wave changes sign when it is reflected. So it is something that we're going to have to take into account in the algorithm that we're going to build. It doesn't matter too much, especially in the case of an echo. In the case of an echo, you're not going to be able to hear any difference if the phase has been inverted or not. However, once we're going to build a simple physical model of a string, it is actually important. That matters, and it's going to change the sound of the string. And same thing with the filter in the room. So if the space is big, and if the reflection, if it takes a lot of time for the reflection to be sent back to you, it doesn't matter if there is the phase reflection or not, because it's not going to screw anything with the, it's not going to screw up with the sound of your thing. But if the mountain is very, 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 very close to you, it's actually going to have an impact on the sound. So we have to think about that. Okay. So actually, I'm going to leave that here. So if I have to draw an algorithm for what I'm going to do here, I'm going to take an input signal. The input signal is going to be the sound of my voice or the sound of anything that I'm going to send to my algorithm. And this signal, well, it's just going to go through anyway, right? Because we want the first reflection, we want the direct signal. So things are just going to, you know, go through. And so the input signal, which is x of n here, is going to be outputted here as y of n, and it's going to go through. Okay. So then I want to model the reflection. Okay. So to model the reflection, I'm going to create a feedback to send the sound of my voice back to the beginning of the algorithm. The thing is, it's taking time here, right? It's taking time between the time I start shouting and the sound is reflected. So I'm going to have to add delay. Very good. So remember the way we wrote a delay yesterday in the z transform, it's going to be z minus power minus n. So n is going to be my delayed length as a number of samples, right? And the thing is, so the sound is going to be sent back to me. But then it's going to be reflected again, and again, and again, and again, and again, and again. So I actually have to add it to the input signal that I'm getting, right? One last thing is, what is going to happen here is that once this reflection that I'm getting here will be processed once, it will be processed again, and again, and again, and again, and again, right? So there is one last thing I need to add to my algorithm.
It's got to decay in some way.
Exactly. In the real world, if I scream here, if I'm shouting at the top of my mountain, part of the energy in the sound of my voice will be absorbed by the air. It will also be absorbed by the mountain. So I'm losing energy every time the sound travels back and forth in the system. So to lose energy in my algorithm, I need to remove energy somewhere, right? How do I remove energy?
Multiply by a decimal.
I'm going to multiply by a number smaller than 1, basically. So by a number between 0 and 1. Okay? It doesn't matter where I put the multiply. I can put it here, I can put it here. It's going to be the same. Okay? It's a linear time invariant system, so I can change the position of those things in the algorithm. It doesn't matter. It's the same. Yeah. There we go. Well, I got my echo algorithm. So in sound engineer terms,
So we actually have to multiply it by a negative number from 0.
exactly, very good. It's going to be a negative number to do the phase inversion. The thing is, actually, in practice, very often echo algorithms ignore that and don't do the phase inversion and just remain positive. This is only going to be important when we're going to turn that into a filter, or we're going to turn that into a guitar string, because we're actually going to be able to turn that into a guitar string, as weird as it sounds. And that's what we call the Karplus-Strong algorithm. Very good. So in that case, it will matter, because in the case of a guitar string, or in the case of a filter, you look at things, the size of your delay length here is going to be very short. In the case of the echo, you want this delay length here to be super, 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 super long, right? It's going to be much longer than one period of the fundamental frequency of the sound that you're generating. So it doesn't really matter. But if your delay length here is smaller than the period of the fundamental frequency of the sound that you're generating, then it's going to have a huge impact if this sign is positive or negative, because there is going to be a phase issue between the signals. So, well, we can test that out. We'll see that it doesn't change anything in practice, but for now, let's leave it positive. But that was a very good point. Any other concern, questions? Yeah. So before we implement that at a high level, because here we're going to try to make a plugin out of that, what we want to do is to have high-level parameters where we can control the feedback of the echo, because that's what we control in an echo, and also the duration of the echo. So the high-level parameters that we're going to have at the top of that is basically going to be a duration in milliseconds or in seconds or whatever. Milliseconds is probably better. And a feedback coefficient. And the feedback coefficient is basically going to be this value here, right? And the closer this value will be from 1, the longer the sound will stay in the system. And the smaller this value, the shorter this sound will stay in the system because it will be damped faster. Okay, let's do it. I mean, we almost have everything that we need, actually. So I'm going to create a function for that. And I'm going to call this function, I'm going to call it my echo because there might be an echo function somewhere already in the library. So just to make sure that it doesn't interfere with what is declared in the library, I'm going to call it my echo. My function echo, well, for now it's just going to be that. I'm going to call it in process so that every time I change something to it, the change is reflected in Faust line. Okay. So first, we take the input signal, right? And the first operation we're doing here is going to be the add. You know, the add of the feedback that we created earlier. So this add here. So the first thing I'm going to put in my algorithm is going to be an add. Okay. So on that side of the algorithm, that side here, I'm not doing anything, right? So I'm not going to have to put anything else than an add on this side of the tilde. So I'm just going to put the add, and I don't have to put parentheses because I'm doing only one operation. Then the feedback, so the signal is sent back. Here I'm going to have to do two operations, right? One delay, one multiply. Because I'm doing two operations on that side of the tilde, what am I going to have to do? Put parentheses, because if I don't put parentheses, then it will probably not work. Okay, so I have parentheses. The first thing I'm doing is I'm adding delay. So I like precision. I want to have a delay that is more than one sample, or have more than one sample precision for my delays. So I'm going to use a fractional delay in here. Okay. And because I'm using fractional delay, I'm probably going to have to import filter.lib because that's where it is declared. Oh yeah, I saved, but I shouldn't have saved. It's okay. So fdelay. Fdelay has three arguments. The first argument is the maximum delay. Very good. So here I have to think about it just a little bit. It's an echo effect. Because it's an echo effect, I want to add a lot of delay. Because I might want to have more than, I mean, it's very rare when you need more than 1 second. Like, otherwise it sounds terrible. But so for now, I'm going to say 1 second. Okay. So the maximum delay has to be a power of 2. Very good. My sampling rate on my system is 48 kilohertz. So the next power of 2 is 65,536. There we go. Okay. The next argument is the delay length as the number of samples. So I'm going to create a variable for that, and I will control this variable with a local slider that I will declare later. And the third argument is the input signal. Okay. So now I have my delay. So the last thing I want to do is to put a multiply. Okay. And I'm going to call it feedback. Here we go. It was pretty straightforward. I want to control these parameters with user interface elements. So I'm going to create my delay length variable, and I'm going to create a slider to control it. And this slider is going to be my, I'm going to call it time. Okay. So it's going to be my delay length, and I want it to be in milliseconds. Okay. So the default, I'm going to say 250 milliseconds, for example. The minimum can be very small. It can be like 0.1 millisecond. The maximum, I said, should be 1 second, so 1,000 milliseconds. Okay? And I can have a precise step of 0.1 millisecond. It should be more than enough. Okay? The output of my slider is in milliseconds. So what is the first thing I have to do before I turn it into a number of samples? So first I turn it into seconds, right? By multiplying it by 0.001. So now the output of my slider is in seconds, okay? And then I just multiply it by sampling rate, okay? So not making the same mistake than yesterday, very good. So now I'm good. I got my delay length as a number of samples. We can smooth it. Yeah. Okay. The smooth here is applied to the previous operation, so to
now being applied to the number of samples.
Yes, so it's applied to the number of samples. And then I need to create the feedback variable, and the feedback variable is well going to be controlled by a slider too. I'm going to call it feedback, and feedback is going to have for now a default value of 0, minimum value of 0, a maximum value of 1, and a very precise stat of 0.001. And I definitely want to smooth it out. Okay? So now if I save that, it should work. So what I'm going to do is I'm going to...
Don't you want less than 1 for the maximum?
No, it's okay. In that case, no, because it's the deal length is very long here. So if the deal length was short, it would be dangerous. But 1 is fine in that case. You just have to be careful, but it should be fine. So now if I play some music, so I got VLC running here. I'm going to disconnect it from my system. I'm going to connect it to Faust Live. And I'm going to connect Faust Live to the 2 speakers. Okay? So no echo for now. But if I increase the feedback, there we go. And I can put 1. In that case, it's okay. Just have to be careful, because at some point,
Does that create a Doppler's effect when you change the delay time?
Kind of. It's a weird one though, because of the smoothing function. If I put more, if I change f delay to be f delay 4, this will probably attenuate this effect. It sounds different, but it's still there. Yeah.
Where's the phase thing? Are you flipping it to?
No, I'm not doing it here yet. But we can do it though. I can multiply that by -1, but it's not going to make any difference at this level. Yeah, see, it's the same. It will make a big difference with a short delay. So if I look at the diagram of that, I can just see pretty well what's going on. There we go. So taking an input signal, sending it back, adding delay, multiplying it by some feedback, inverting the phase, feeding it back. Okay? It works. Yes? So the 4 after f delay is the order of the interpolation that you use for your fractional delay line. So it will give you more precision, basically, and it will prevent artifacts from happening in some cases, but f delay is fine for what we're doing in the frame of the workshop. F delay is second order interpolation. Cool. Any other questions?
Is there a simple way to put just a dry signal level or to control the amount?
Sure, absolutely. That's actually a very good question. So that's the next thing that we can do. So so for now, our plugin has an input, has an output, and the output is the output of the effect. Very often on an echo pedal, on a guitar or something like that, you want to be able to control the dry, wet parameter, which is basically the amount of that you want and the amount of that you want. Actually, that's a great exercise. So you guys are going to try to add this parameter. Okay? So what I want basically is just so that we all agree with what we're going to do. So at a higher level than that, I've got my input signal, okay? Then what I want to do basically is to split my input signal into two signals. One is going to go in my echo effect, right? Then here, I'm going to have some kind of multiply. That one is just going to go through. It's my dry signal. It's going to go in some kind of multiply. And then I'm going to merge those two signals together and output the result. And then here, I'm going to have something very similar to what I was using for the panner, basically, right? Where I'm going to have a variable, and this variable can be, for example, dry, okay? And so if I call this variable dry, then what I will probably want to do is to multiply this signal here, which is the dry signal, by dry being a number between 0 and 1. Very good. And then here I want to have something where I do 1 minus dry, right? So that's When dry is 0, I get only the wet signal. And when dry is 1, I only get the dry signal. Okay? So you guys can do that. That's the first exercise of the day. And you want to control the dry parameter with a slider, of course. Should be quick. Okay. So, here is a solution. This solution should work pretty much for everyone. So I'm going to put that in the echo function. And so the first thing we want to do is that we said we're starting with one signal, right? So it's 1 underscore. Then we're splitting the signal into 2 different signals. One that goes to the echo algorithm, which is that, okay? And one that is not being processed. So I'm going to put an underscore and a comma, okay? Then I said that I want a dry, wet parameter. Here I'm going to call it dry. So what I'm going to do is that, because here I get the dry signal, and I'm going to control the amount of dry signal that I want to add to my mix, I'm just going to do a multiply here by a variable called dry that I didn't declare yet. I will declare it afterwards. Okay. And then I'm going to multiply the output of the echo, which is this entire operation here. So actually, to make things even more clear, I mean, you don't have to do that, but just to make things more clear in that case, I can put parentheses in here. Okay. And then I can just send that to a multiplication by 1 minus dry. Okay. That way, I've got 2 independent blocks. This one.
The left parent shouldn't be before the F delay.
No? Well, I'm just putting the parentheses here to make clear that I have 2 blocks. I have this block here.
But instead of this
Okay.
And this block here. Like, in other words, I do the split, okay? My split is splitting the signal into 2 different signals. This one and this one. I'm just putting the parentheses here to make clear that I got 2 blocks, okay? And then have signal 1, signal 2. I just want to add them together and to merge them into one signal, okay? So the last thing I need to do is to create a dry slider. So I'm going to create a new slider. It's a horizontal slider. Its name is dry, and its default value, I'm going to say 1, okay? Just to get dry signal, minimum 0, maximum 1. Step 0.01, and a smoothing of it so that it doesn't click. Good. So I can try. It's very annoying because VLC always disconnects from jack, so I need to do that. There we go. So right now the signal is dry, but here we go. What I like about the echo effect is that it's so simple and it sounds so good, you know, like whenever you start using it, then it's like, you know, it's incredible.
That carpal strong sounds pretty realistic.
That's true. Yeah, that's what we're going to do next. Good. So, so that's the case of. So here we got an echo. So so that's the case of a very, very big space, right? It's a space outside. It's not a room, right? So now let's say that we want to modify a little bit this algorithm so that instead of modeling a very large space, we model something that is smaller. So something that is actually more like a room, like this room here. What do we have to change to our algorithm so that we model basically a smaller space? How do we change the size of the space that we're modeling with the echo here? Yeah, we change the delay time, and we make it smaller. Okay. So we'll see that all these things are very connected to each other. Echo is the same algorithm than for a string algorithm, than for a filter, basically. So what we're going to do now is that we're going to go back a little bit in time to what we did yesterday. And we're going to turn this algorithm that we have here into a filter. Okay. So here we have the extreme case where the delay length is very long. If we make the delay length very, 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 very small, actually, if we just totally remove it, what is going to happen? So in other words, if I keep this algorithm in here and I remove that, we said that we have still a one sample delay in here because of the feedback. Now someone has an idea of what's going to happen then. So we remove the delay.
So that's our very flat low-pass filter.
So that's, yeah, so the low-pass filter that we studied yesterday is what we call a feed-forward filter.
So this will be an IR.
Because the signal always go forward, never goes back in the algorithm, right? Here, we're going to be able to build a different kind of low-pass filter. And this kind of low-pass filter is what we call a feedback filter, because instead of being a feed-forward filter where the signal always moves forward, in that case, the signal is sent back in the algorithm, right? And that's the big difference between the two kind of filters that we talked about yesterday. One of them is called an IIR filter, and the other one is called an FIR filter. So FIR stands for finite impulse response. And the reason why feed-forward filter is an FIR filter is because if I send a sound in this filter, after a very short amount of time, the sound disappears and is not in the filter anymore, right? Well, with this algorithm that I have here, which is my echo algorithm, that I can also consider as a filter, because of the feedback and of the loop that I created, the sound stay here indefinitely, basically. It doesn't stay here indefinitely if my feedback is equal to 0, right? Because then there is no feedback. But even if the value of feedback is very, 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 very small, like 0.00000001, even though the sound is you're not going to be able to hear it for very long, in theory, it will stay here forever, stuck here forever. Because even though I multiplied by 0.000001 every time, it's still there. It's the amount of energy that I have is totally neglectable at some point, but it's still there. And that's why we call that an IIR filter. It's infinite. And mathematically speaking, if we have to express that kind of filter, it will always keep the energy that you send in it, even though at some point it totally you can't hear it anymore. But in theory, it is still there. Okay, so no problems. So these kind of filter so they all have a lot of names, right? So we said IIR, FIR filter. IIR is also a feedback filter. IIR is feed forward. Okay. But in more signal processing terms, and that's where I'm not, and that's where I will stop, because I will not go further after that. They have a more technical term, which is, so that one is,
Moving average.
so that one is a moving average, but it's, okay, that's another one, but that's not the one that I wanted. That one, the one we studied yesterday, is what we call a 1-0 filter. 1-0. It's also a moving average, indeed. And that one here is a one pole. So if you like maths and you want to know why this is called one pole and why this is called 1-0, you read the book. And all I can tell you is that that is very, very, very correlated to what is at the top of the board here. So just very quickly, this thing. No, this thing was supposed to have, oh, it's a very weak laser. Okay, whatever. Okay, so the difference equation that is at the very, very top of the board is, as a matter of fact, is an equation for a filter. Okay. Well, actually, there we go. It's an equation for a filter. And we see that the output of the filter is y of n, okay? And the input of the filter is x of n, okay? So we see that in the equation, we have both x of n minus something, okay, and y of n minus something. So any filter can be represented by the direct signal that it has in it, which is x of n. So in other words, if we discard that part of the equation, then we have the generic equation for feed-forward filter, because y of n is equal to x of n something, okay? And x of n minus something, and the minus something is the delay, right? Okay. And then the multiplication that we had before that with b, so I don't know if you remember, but yesterday that's how we called it, b. That's what we call the zeros of the filter. So those are the coefficients of the filter, but of the direct signal of the filter. Okay, so the feed-forward coefficients. Okay. And that's the filter that we built yesterday. Is called a 1-0 filter because it only has 1, 0, right? It only has one delay, right? And we call the filter that we built yesterday a 1-0 filter because it only has one B, right? If it had multiple B, then well, it will be a multiple 0 filter. Okay. This filter here, as a matter of fact, has actually, well, it doesn't have, well, it has a 0, but the 0 is it's B0. Yesterday we called the 0 that we had B1 because B0 in general is ignored. Here that's all we had, so we ignore it too. Okay. But then on the other side of the equation here, I got the feedback signal, which is y of n minus some kind of delay. Okay. And I have also a coefficient in front of it. And this coefficient is called if on one side it was called a 0, on the other side it's called a pole. Very good. So the B's are the zeros and the A's are the poles. The B's are the feed-forward coefficients. So the coefficients of the signal that always moves forward and never goes back. And A is, well, the A's are the coefficients of the signals that go back in time or go back in the algorithm. So it's, if you want to know more about that kind of things, you should read the books. Like, because in general, in Julius's class, the class that Julius teaches here, signal processing at CCRMA, students only get to that point after 1 quarter. You know, so you didn't have all the background before that to get there. So it's just that I'm trying to kind of put in a relation with what we're doing, you know, like, but if you want to learn more about it, you should read the books, you know, because here we're skipping a lot of steps before you guys can actually get a very good understanding of what we have here. Does that make sense? Very good. Cool. So we're going to turn that into a one-pole filter, as a matter of fact. So I'm going to get rid. You know what? I'm just going to save that. You know, comment that out, and we're going to start over with something new. Now I'm just going to copy and paste that because we're going to hack it. I'm going to call that my one pole. Okay. So what I'm going to do here, just for now, I'm going to get rid of the delay, okay, so that we only have a one sample delay. The one sample delay implied by the feedback, okay. So I'm going to get rid of that. And now I'm going to put parentheses. Actually, I can do that too. I can do minus feedback, and that works. Okay, and my good in terms of parentheses, I should be good. Okay, so if I save that, I'm going to turn the feedback to 0 for it. Because now we're playing with FIR. Because now we can create very unstable systems. Because in the case where feedback would be equal to 1, so in the case where, so feedback in that case is my pole, right? It's the pole of my filter. So I actually want to rename it. I'm not gonna call it pole because it's a bad name. I'm gonna call it A1. Okay, because that's the first pole of my filter. Okay, that is totally ignored for now by the system because actually I'm just gonna get rid of it. But it would have been ignored, and dry is also ignored. So I'm gonna get rid of dry. Okay, I'm gonna get rid of everything. There we go. There we go. And there we go. Okay, and I'm gonna get rid of that too. Get rid of that. Get rid of that. And feedback is not feedback, it's A1. Okay? Did a lot of cleaning there. So, now if I save that, it compiles. It's a good sign. Then I will look at the, okay, no, bad idea. Okay, not yet. So I've got the code here. What I'm going to do is that to test it, and I'm actually going to change A1 so that A1 can also be a negative number. Okay, because a pole can be positive or negative. And then what I'm going to do is that I'm going to send noise in it because that's the only way to actually see what it does on the spectrogram. So I'm going to save that. And I got noise, okay? And I'm going to start Beltline to look at the spectrum of the sound that I'm computing right here. So the point is that we turn that into a high pass or a low pass filter, okay? And I don't know if you noticed, based on the sound that we're generating here, but it's a much more effective one than the one we had yesterday. The one we had yesterday was very tame. Here, it's a very, very aggressive high pass or low pass filter. You should be very, very careful with the coefficients that you use now. Because the problem is that if you get too close to 1 or too close to -1, then you create an infinite loop and you're adding energy all the time in the system. And then it becomes unstable. And that's actually, that we can see in Beltline, the whole thing just breaks. And the whole thing just breaks here. Actually, do you know why we're getting that? There is actually a reason why. No, it's just a gigantic DC offset, basically. We're getting a gigantic DC offset because the problem is that the signal gets very, very, like the gain of the signal gets extremely high. And because it gets extremely, extremely, extremely high, then the signal just starts totally clicking and is raised up to 1. And actually, the spectrum analyzer sees that well. It sees that, yeah, that's DC here. That's like 0 hertz. And sometimes it manages to get rid of the energy and to come back. But what we see here is just a huge DC offset. So we have to be very careful when we manipulate that kind of filters. So actually, just to finish with that, so we all agree that this is what we wanted, right? Because we have a feedback. The delay is not written anywhere here, okay? But it's implied because so we have a one sample delay, right? So in other words, if I had to write the difference equation of this little filter that I just wrote here, okay, I'm gonna get rid of that. The difference equation would be y of n equals x of n plus minus y of, well, actually, I forgot the, yeah, there we go. A1 y of n minus 1, right? We'll agree with that, right? A1, because I'm multiplying the A1 here, I'm n minus 1 because there is a one sample delay, and x of n is the input, the direct signal. Okay. So if you go on Julius's website, there is a very nice page about all these things. So if you just Google JOS one pole, the first link, which is this URL here, is So that's the one-pole filter. And that's exactly what we just did. Okay? And we see here that we have A1 and we have B0. But B0, we always ignore it and discard it so that it's equal to 1, right? Okay. So you will notice in the difference equation that Judith wrote on his website that A1 here has a minus sign. It is negative. Well, here they put a plus and a minus. Well, there is a mathematical reason why we say that it's negative. I'm not going to tell you why because it's complicated. All I can tell you is that it's related to the fact that mathematicians assume that there is a sign inversion in the signal when it is reflected. Okay? And that's why there is a negative sign here. So here we can see the frequency response of this filter. We see that this filter is a low-pass filter when A1 is equal to minus 0.9. So it is a low-pass filter when this guy is positive, basically, right? Because in that case, if A1 is equal to minus 0.9, it interferes with the minus sign that we have here, becomes a plus sign. So when that is positive, then it's a low-pass filter. When that is negative, it is a high-pass filter. Okay? So when A1 is equal to 0.9, then it becomes negative here. So the feedback signal is negative. There is a phase inversion. And so now we have a high-pass filter. Okay? And that one is way more aggressive than the one we had before, as we can see. And it is actually removing frequencies now. Very, effectively, not like the one we had before. Before we go to lunch, just to finish a little bit on that, this is just going to work the same way than what we had for the 1-0 filter. Now if we increase the delay in the filter, so instead of having a one sample delay here, we add more samples. The same thing than yesterday is going to happen. So if we had to plot the frequency response of this filter across the entire spectrum, okay, it would really look like that. So dying, and then, So it is also a calm filter, okay? It is just like the 1-0 filter that we had yesterday. So it is a comb filter, it's just that we can't see the teeth of the comb yet because they are out of range. They are after the Nyquist frequency. By the way, we still consider that this here is the Nyquist frequency. Okay? So pi is the Nyquist frequency. Does someone has an idea about how the comb is going to look like now, based on what we see here? Still going to look like a comb. Like the spectrum is still going to look like a comb. It's just that this comb is going to have a different shape. Absolutely. The teeth, basically, of the comb are going to be much, much, much narrower. Because yesterday, I don't know if you remember, but it looked like that, basically. Now it looks like that, okay? So instead of having a frequency response for our comb filter that will look like that, basically, woof, 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 woof. Now it's going to look more like that. And it's basically the opposite. So that's what we'll do this afternoon. When we will try that, we'll see that it's very effective and that it's so effective that it will really create harmonics this time. So at this very tip here, we're only highlighting one frequency. So, so that kind of filter will really sound at some point like a square wave, basically, if we sound it noise. Any questions about what we did this morning?